In this section, we're going to take a closer look at variables that we can measure and describe for a gas. So I'm listing 4 variables here that we commonly work with when we're dealing with matter in the gas state. These 4 variables are volume, temperature, amount of gas, which is usually expressed in moles when we're doing calculations involving gases. So again, volume, temperature, amount of gas expressed in moles, and the 4th and final variable, pressure. Now we have spent a lot of time so far in this semester looking at volume, temperature, and moles, and units with which we measure these variables, these quantities, and how to do calculations with them. We haven't spent as much time talking about pressure, so I will do that in just a minute. But before I go to pressure more closely, I just want to state that these 4 variables that are listed above completely define the state of a gas, meaning once you have specified, measured, determined any 3 of the 4 variables, you have also determined what the 4th variable must be. So what that means is that if you tell me, here is a gas, and I'm going to tell you what the volume and the temperature and the mole amount of the gas is. Once you have given me numerical values for 3 of these variables, in this instance volume, temperature, and mole amount, you have also determined what the pressure of the gas has to be. It can be calculated. So once you specify any of these 3 variables, you have determined what the 4th has to be. If you tell me what the pressure and the moles and the temperature of a gas is, I'll tell you what the volume of the gas is. You have determined that as well. So let's take a closer look now at the 4th variable that defines a gas state that we really haven't looked at much so far in our discussion of chemistry to this point, and that is gas pressure. As we looked at with the kinetic molecular theory of gases, gas pressure is the result of the collision of gas molecules against the walls of their container. So what I'm showing here is a container in a box shape, and this red dot represents a gas particle. Of course, there would be many gas particles in the container, not just one, but I want to focus on this one gas particle. It's moving rapidly in straight lines. When it collides against the container, it exerts a force due to its mass and its velocity against the walls of the container, and when it hits the container, it will bounce off and continue to move in a straight line in some other direction, right? So we can see here as we fill this container with a gas, we're going to have many collisions happening with the gas molecules or particles against the walls of the container because they are moving rapidly and colliding against the container walls. Here is the mathematical definition of pressure. Pressure mathematically is defined as force applied over unit area. That's what pressure is, the force applied per unit area. So if I push down hard on a surface with my hands, I'm exerting a pressure on that surface, right? Applying a force per unit area. It's easy to see when we look at this equation that we can increase the pressure of a gas by either increasing the numerator, the force, or decreasing the denominator, the area. So if you want to increase the pressure of a gas, you can do that by increasing the force, which means you either increase the temperature. Remember from the kinetic molecular theory, as you increase the temperature, gas molecules are moving faster on average because of their greater average kinetic energy. and they'll collide more often and more forcefully with the container wall. So you're increasing the force when you increase the temperature of a gas. You can also increase the force by simply adding more gas molecules. Keep the temperature constant, but just put more gas in. More gas molecules, more collisions, more force applied, right? You can also increase the pressure by decreasing the area that the gas molecules are colliding against. So if you decrease the overall volume of the gas container, you will have more collisions happening per given unit area of the container walls. So if I came over here and just kind of highlighted this square patch, right, a two-dimensional patch or area, if you decrease the volume, then you will have more gas molecules colliding in a given unit area of the container, and that will increase the pressure as well. So we can begin to see relationships that are existing between these variables that describe the gas state. The most important gas system that we have to deal with and understand is this gas system that we are born into and live our lives in, which is the atmosphere that surrounds the Earth. Without doubt, that is the most important gas system that we need to know and understand. So the atmosphere is a mixture of gases, primarily nitrogen gas and oxygen gas. Those are the two primary gases that make up the atmosphere. Nitrogen is found in about 78% by volume in the atmosphere. So out of every 100 liters of atmospheric gas, nitrogen makes up about 78 liters out of that 100. Oxygen is present in about 21% by volume in the atmosphere. So nitrogen number 1, oxygen number 2. Notice 78% and 21% add up to 99%. So all of the other gases that are found in the atmosphere, such as argon, carbon dioxide, all of the rest of the noble gases, water vapor, all of these other gases are present in the atmosphere in much smaller amount than either nitrogen or oxygen. Atmospheric pressure is defined as the pressure exerted by the mass of this enormous gas system that makes up the atmosphere, the pressure exerted by that mass of molecules on the Earth's surface. And we need to measure the pressure of the atmosphere. It can change based on location on the Earth's surface. Atmospheric pressure is greater at sea level, for example, than it is at the top of a mountain. A barometer is a device that measures atmospheric pressure, and I've given you just a simple schematic of a barometer. It's also found in your textbook, right? So you take a long tube and you fill it completely with mercury, which is important because it's one of the few metals that's a liquid, and it's also a very dense metal. If you fill the tube completely with mercury and then invert it into a dish of mercury, some of the mercury runs out of the barometer, but most of the, runs out of the tube that makes up the barometer, but most of the mercury remains inside the tube. It doesn't just completely run out. Right, so the dish is full of mercury, the tube is full of mercury. Mercury is a very dense metal in the liquid state, so this column is exerting a force because of the mass and gravity acting on it. Why doesn't that mercury just run right out of the tube into the dish? Well, the answer is atmospheric pressure. The pressure of the atmosphere is acting right here on the surface of the mercury and exerting a force that just holds that mercury column up inside the tube, right? So you're seeing the effect of atmospheric pressure exerting a force that's just pushing the mercury up inside the tube. Notice that above the mercury, there's what we call a vacuum, just empty space, so no force here, right? The atmospheric pressure is just pushing that column of mercury up. So you can take a measuring device that measures length, a metric rule, and measure the height of that mercury column. As the atmospheric pressure increases, it pushes the mercury up higher and higher inside of the tube, and the height increases. So we can say here that the pressure exerted by the atmosphere is directly proportional to the height of the mercury column, and in fact, that's one of the units used to measure pressure, millimeters of mercury. In other words, what is the height of this column expressed in millimeter units? So that is how a barometer works. And let's go over here now and take a look at units with which we can express a pressure reading. We will use 3 common units in this class, right? And those units are millimeters of mercury, torr, abbreviated TOR, and the last one, ATM, for atmospheres. So the relationship between these 3 commonly used units here in this class are 760 millimeters of mercury is equivalent to 760 torr. So what that relationship tells you is that the unit of pressure exerted by 1 millimeter of mercury is equivalent to the unit of pressure exerted, or the amount of pressure exerted by 1 torr. A millimeter of mercury pressure unit is the equivalent magnitude as 1 torr, right? 760 millimeters of mercury equals 760 torr, and that is equivalent to 1 atmosphere of pressure. These relationships are all exact, so sig figs don't apply. And you remember that whenever we have an equality, we can use this and make a conversion factor. Before I do a calculation involving converting from one of these pressure units to another, I just want to mention that there are some additional pressure units. We just won't work with them commonly in this class. One of those is called the Pascal, abbreviated PA, capital P, lowercase a. And interestingly, this is the SI unit for pressure. But it's not a terribly convenient pressure unit to work with, so we will not be using it often in this class, but it is the SI unit of pressure. The other pressure unit I'd like to mention is a pressure unit known as PSI. And PSI is an abbreviation of pounds per square inch. Pounds per square inch. Pounds is a unit of force, and inches squared is a unit of area. And PSI is important to note because that's how car tire pressure is measured, right? So if your car tire pressure is measured with a device, either you do it or you take it to an auto shop that maintains your car, they will check your car tire pressure every time you bring it in, and the unit that they are measuring that pressure is in PSI, pounds per square inch, or pounds per inches squared. So before we finish this discussion, let's just do a quick conversion from one pressure unit to another. So if a pressure is measured in millimeters of mercury, 942 millimeters of mercury would be equivalent to how many atmospheres of pressure? Well, here are our relationships. We see that we can make a conversion factor. 1 atmosphere equals 760 millimeters of mercury. So right down here, we do a very straightforward dimensional analysis problem. 942 millimeters of mercury. Here is my conversion factor. 1 atmosphere to 760 millimeters of mercury. Millimeters of mercury units cancel. I'm left with an atmosphere unit. This conversion is exact, so sig figs correlate to the data that was given. 942 millimeters of mercury is equivalent to 1.24 atmospheres of pressure.